All right, so the intro is, there's plenty of books around AI stuff. And when I started to explore this area a couple of years ago, I was stunned by, yeah, they go into a lot of details about how the algorithm works, but they don't talk about the impact. So what will this mean, like, on different levels? And that's what I want to explore a little bit in this presentation. Hence the title. So what would this mean for CTOs and the engineering process? So if we jump into it, if you are an AI expert and a data scientist who's done this for years, this presentation probably not for you. But if you want to explore the boundaries of AI and how this is going to impact your surrounding, this will be useful. So I'm going to pull up a couple of use cases that are already there in how AI is being used. Everything from autonomous cars, percepting what's happening around the car. Is this a pedestrian? Which way is the pedestrian walking? Is going to cross my path? Things like this, AI is already using. It's also used to detect fake things, like fake art. It's a well-known component of recommendation engines. A data point is that roughly 30 to 40% of all the purchases at Amazon today is done through the AI that Amazon has for recommendation. So that's quite a lot of money that's been earned by the AI. And of course, there's tons of different examples of how AI is being used. Now, I want to show you a little example just to give you an idea of what an AI can do, and by showing a small video. And it also demonstrates some surprising things that the team that developed this AI found out in the process.
And the results are magnificent, amusing, weird. You'll see in a moment. These agents learn from previous experiences, and to the surprise of no one, for the first few million rounds, we start out with pandemonium. Everyone just running around aimlessly. Without proper strategy and semi-random movements, the seekers are favored and hence win the majority of the games. Nothing to see here. Then, over time, the hiders learn to lock out the seekers by blocking the doors off with these boxes and started winning consistently. I think the coolest part about this is that the map was deliberately designed by the OpenAI scientists in a way that the hiders can only succeed through collaboration. They cannot win alone, and hence they are forced to learn to work together, which they did quite well. But then something happened. Did you notice this pointy, doorstop-shaped object? Are you thinking what I'm thinking? Well, probably, and not only that, but about 10 million rounds later, the AI also discovered that it can be pushed near a wall and be used as a ramp, and ta-da! Got him! The seeker started winning more again. So, the ball is now back on the court of the hiders. Can you defend this? If so, how? Well, these resourceful little critters learned that since there is a little time at the start of the game when the seekers are frozen, apparently, during this time, they cannot see them, so why not just sneak out, steal the ramp, and lock it away from them? Absolutely incredible. Look at those happy eyes as they are carrying that ramp. And you think it all ends here? No, no, no. Not even close. It gets weirder. Much weirder. When playing a different map, a seeker has noticed that it can use a ramp to climb on the top of a box, and this happens. Do you think couch surfing is cool? Give me a break. This is box surfing. And the scientists were quite surprised by this move, as this was one of the first cases where the seeker AI seems to have broken the game. In a few isolated cases, other interesting behaviors also emerged. For instance, the hiders learned to exploit the physics system and just chuck the ramp away. After that, the seekers go, "What? What just happened?" But don't despair, and at this point, I would also recommend that you hold on to your papers, because there was also a crazy case where a seeker also learned to abuse a similar physics issue and launch itself exactly onto the top of the hiders. Man, What a paper!
All right, just to give a small illustration of that already when being trained, AIs today find ways to break rules and find solutions which we even don't even imagine. And I think if you look at the AlphaGo system, the DeepMind system, and the way that the AI is acting when it's beating the current world champion of chess or the current champions of StarCraft, you'll see similar things happening. So already today, AI have actually moved our understanding of how to play chess and also Go. So with this said, AI is not a universal better solution. Some things do not turn out so well when you give it to an AI. For example, they're making this recipe, which is just asking AI to make a recipe. So AIs, to summarize, they are not aware, and AI is not imaginative, and AI is not self-learning. So even though it can push the boundaries and teach us things which we didn't see, we have to understand that they are actually carefully engineered so far by people to perform a specific task. That said, this is the current state. What is maybe more freaky would be if, for example, we found ways which we can teach the AI to self-learn. Then this would, be a completely different ballgame. But that's how it looks like right now. So this is interesting because if you take a data-driven approach and you accumulate a lot of data, this is a good asset, but it needs to be used. And here's where AI becomes interesting. So that said, let's compare AI and especially machine learning with traditional software development. So if we make a very simple example here of a software developer trying to understand what type of number did someone write here based on an image, we would normally define it, we will model it, we will write some rules, we will test it, and we will deploy it. The trick is that that makes an awful lot of rules to figure out if this is number 3 or not, because there's so many use cases out there. So the difference here when we employ AI here is we take these 2 steps, model the world and rules, we take them out of the equation and we say, what if we teach a computer to do this? So we define the problem, we give it tons of data, and we'll let the computer figure out how to understand this data and produce an outcome. Is this a 3 or not? And based on those tests, and we repeat them many, many times, we can actually reach a very good accuracy on this number. So if you would look into how the workflow happens when this is being developed, and we look a little bit under the hood, there are a couple of phases that we go through. So first phase is it's basically access and explore data. Sensors, databases, files, it's just getting the data. Then there's a step of pre-processing where we actually need to make the data ready to be used. Clean it, filter it. We might make some transition and normalizing on it. And then the real work start with actually making a guess on what type of algorithm and model that could be useful to create the prediction, and do some tuning on it and test that this actually produce a good result. And the majority of the work takes part in the 2 first steps. The third step is iterative, but the first 2 steps is really where the emphasis goes. And of course, we're going to deploy this. So if we will illustrate this with a small example, imagine that you have a smartwatch, a device, and you want to figure out if the person that has this device is biking or not. So the first thing you would do is try to collect data. So just acceleration data and store this in some database. And in the beginning, you might not even do anything more advanced than just try to explore this data. So you use visual tables, visual means just to understand, does it tell you anything? Then the next step happens, and the first thing that you normally need to do is normalize the variables. So normally, you will get a matrix of different variables, but you do need to normalize them. Most models actually requires this for this process to work, or actually give good predictions. Then takes a step of feature engineering. And to illustrate this, imagine that you would have a vector with two parameters telling you acceleration up, forward, and to the side. You might actually create another feature, which is the velocity forward, which is just a function of acceleration forward over time. And you might also add into this vector the end result, a label. Is at this point the person on a bike or is it not? Based on this feature engineering, you will then pull this matrix into your model and you will try different algorithms on it, just to tell whether it can predict if the person is biking or not. And then you'll do model testing. So you will check how accurate the prediction is, and if it's not accurate enough, you'll go back again, do some parameter testing, change the model until you're happy. And finally, you'll take the model and you deploy it. Maybe you deploy it as a service on the cloud, and then you can go on a web page. The user can find out the number of days the person's been biking versus number of days the person's been watching TV. So just to give a small illustration of how this process actually works. This said, where is AI then very useful, or where does it excel? It excels when you want to do real-time predictions. So imagine that you are going to do you're asking for a loan and you want to figure out if we should give the credit or not. But you do want to deliver this within a second or two, or just very, very quickly. That's where AI is really, really good. The second area with AI excels is if you have multiple non-linear dependencies. So you have many variables and they are sort of dependent, and it's really hard to untangle. Then AI is an excellent way to get some type of modeling of these dependencies. And then finally, get high accuracy. Now, there is a crux here, and the crux is that you do need to have quite a lot of data normally for the prediction to be good enough. So let's go a little bit under the hood, and let's just look how AI works and what type of frameworks that exists. So how AI works is that you have an algorithm that makes a prediction. It could be what the speed is, the acceleration is, but it makes a prediction. And then the other component is that you have a cost function that actually figures out how close were you to the original prediction. So this could be a plus or minus, it could be a square difference. And finally, you have an optimization function that tells you if the error is very good, go back and change some parameters of the algorithm until we get closer to the expected value. Now, the interesting thing is the math in the algorithms are normally very, very simple. It's not very advanced stuff. The interesting aspect is that with a very good optimization function, you can get pretty good predictions, even though the math in the algorithm is actually pretty straightforward. If you look a little bit on the types of frameworks and techniques underneath here, you'll find three areas: machine learning, deep learning, and reinforcement learning. If we take these two components and we split them up, you'll find that actually they solve problems in two ways. So the first thing, and yes, in AI, there's a lingo, like there's a terminology for everything, and you'll get to see some of this now. Supervised learning is when you have the result. You are the trainer and you're training the machine to make a prediction. In the unsupervised learning case, you are giving the machine a bunch of data and you ask the machine to figure it out. Basically, it's a clustering question where you ask the machine, do things belong together? Do these look like cats, or do cats do the pets, or do they have different classes of pets? But you don't tell the machine how to figure this out. And finally, you have reinforcement learning, which is where you have actors that do things. If you go a little bit underneath the hood, you can think of the supervised learning can be split into two types of problems. The first problem is that when you want to make a continuous prediction, a linear number, or continuous number, or a classification, which is this a flower, or is this a pet? Those kind of things. And I mentioned before, unsupervised learning is clustering. Like, how do things belong together? And if we look at some examples of this to give an illustration, classification, you'll see things like spam filtering, it's a good example, image detection, fraud detection. Continuous prediction would be, give me the predicted price of sales or real estate, the stock price, or how long until I need to go take the car to a service. Reinforcement learning, this is where you have real-time games and also another version of recommendation engine. And the difference between the recommendation engine in the classification case and the reinforcement case is that in the latter, the reinforcement engine would make the decision of what to recommend based on your latest action. So by just saying you pull something into the shopping cart and took it away, and you repeat this pattern, the reinforcement engine would discover this and say, maybe this guy doesn't know what to buy. So maybe we should give this guy a recommendation for what the general purchases is. If you then compare these different approaches, and you might say, is one always better? No, not really. In the machine learning case, the benefit is that you get a pretty good accuracy with not so much data. Whereas in a deep learning case, which is the case of using neural networks, you'll get to higher accuracy. However, it comes as a cost, with a cost. You need more data and you need more time. So think of that the performance actually increases logarithmically with sample size. That's sort of the general rule, at least in this case when we look at image detection. So when to use which? In machine learning, that's when you want to have quick results and you have limited data. Just a number of hundreds of data points might be enough for simple models to make a decent enough prediction. Another important case for the machine learning is that you can actually explain how the prediction came about, which is sometimes required by compliance on safety regulations. Deep learning, where you have your neural networks, here you have plenty of data, and we might be talking millions of data points. Very slow to train. We can talk somewhere in the range of hours to days. And it's a black box. So it will make a prediction, but there's no way you can figure out how it came about to make that prediction. And reinforcement learning, that's deep learning on steroids, so even slower. But more importantly, this requires a lot of time and effort to train. So if you take the AlphaGo scenario, I mean, the team might spend a year or 2 years before it actually deploys this AI in a real environment. So what does this mean then for architecture? The first thing to realize is that this architecture makes a difference when you start to scale. So if you want to do some lab exercises, you have a few people, they want to test run things. I mean, that's fairly simple. But it's when you start to scale this, then you actually need to think about how the architecture is created. A few areas that you need to consider. The first is security. It's worth noticing that if you collect data and you put it in a central place, which is a pretty good starting point to fuel AI, it's important to notice that with a lot of data, even though you anonymize this data, even a normal human being can make some predictions of, for example, who this is. So if you give enough data points on my GPS position, you can probably predict it's me, even though it didn't really tell. The second part is reproducibility. So I mentioned before that you do quite a lot of data operations on your data stores, and you need to find a way to reproduce this. So I'll do a lot of ad hoc operations in my local data store, and I need to find a way which I can scale this out on my data store, and make sure I don't lose them once I've created them. The first point to think is portability. And the idea is that you train a model, but then you want to be able to deploy it to many different areas. You might have different tech frameworks that you want to work with, and you want to make sure that whatever architecture you've chosen supports this portability. And this also becomes the case when you think about how to actually train a model. So does the architecture enable you to parallelize the training so it doesn't take a lot of time? And finally, the point of agility, thinking that once you train a model, you put it in place, you want to find a way that makes sure you can do versioning, you can detect if the predictions is getting worse, drifting, and the ability to retrain the model once it's gone live. So are there different tech stack examples that support this? Yes, of course. And there's a lot happening in this area right now. But I'll highlight two of the main ecosystems out there. The first worth mentioning is MATLAB. So I'll draw an arrow here to illustrate the different phases which these tech stack supports. And MATLAB, you probably stumble upon some time during your, if you spend time in university. The good thing with MATLAB is that it's very quick way to have very fast iterative cycles throughout this process. And you can actually use MATLAB to deploy your models either directly onto cloud servers. But interestingly, MATLAB also allows you to do code generation of your models and deploy them as built-in systems, for example, in the car. The second ecosystem that is very worth mentioning is the Python ecosystem. And here you have tools like scikit-learn, which is sort of the machine learning box inside Python, TensorFlow, which is the deep learning path, the neural network, and Keras, which is a high-level API on top of TensorFlow. This can be used to actually, after you've trained the model and you completed all the steps of prediction, deploy them to the cloud as a REST API, for example, using Google Cloud Machine Learning Engine. Of course, there are other cloud environments, and you can also choose. But this is the one what I've found is the one that's is best currently developed to support the Python ecosystem. So is this a game changer then? And if so, how? So let's speculate a little bit. So I'm going to show you some example of what this could mean, and think of this as take this with a grain of salt, but also think that there may be some truth in how this might emerge. So now I'm going to take a step back and look at history and how we have used automation. Throughout time, we started with doing repetitive manually tasks. We moved them into machines. Then we taught the machines to do calculations somewhere around the 70s, 60s, 70s. And the last number of years, we spent a lot of focus on digitalizing the workflows. However, and we can say fairly easily that today computers and robots, they do this part better. They do this better than humans today. But what we always kept close to our hearts is the decision making inside these processes. And our assumption has always been humans do this better. But now the game is changing. So that was pre-AI. And it's very simple to say that already a huge portion of the decision making inside our digitalized workflows can be moved to and done by computers. That doesn't mean that they should or can do everything, but the interesting thing is the majority they can already do. So how does this affect us? So let's look at 3 different roles here. Let's first look at the developer role. And the first thing to notice is that a large part of developers' roles of writing rules, business rules, actually already we can use the machine learning and AI to figure this out. We still need developers, definitely, because we'll need to develop the pipelining and the ecosystem and a few rules. However, we don't need developers to write all the business rules anymore. And then let's explore how this will impact a business owner. And I'll give you a very simple analysis, data-driven development analysis. And I use the Swedish Social Insurance Agency, or what we say Försäkringskassan in Sweden, as an example. And when I do this, I want to emphasize that I do this because people know about it, and it's very familiar to you if you are here in Sweden. This said, I could have pulled any example. I could have put a bank or an insurance company, and you probably see something similar happen. But the idea is that of the Swedish Social Insurance Agency is that, okay, you might get sick, you make an application to get some funding, refunding back, to get some money during the time you're sick. And in the end, the Swedish Social Insurance Agency make a decision, you get the money or not, and pay it back to you. Now, if you look at the services, and I've now explored the services that they list towards private people or people, public citizens, individual citizens, it's very interesting because roughly 81% of all the services that are already out there today can be completely automated. Roughly 50% partially, and 4%, I don't know. And what does this mean? Well, for example, if you're a person that is sick, the lead time to get sickness compensation today is 120 days plus, and it's growing. And what does this mean? Well, it means that during this time, you don't have any income, you get worried, and you spend a lot of time on the phone asking what's happening with my issue here. Another thing to pay attention to is the staff. So today, Försäkringskassan have 14,000 employees in Sweden. And if we turn this into what could it mean if we deployed AI and digitalized processes? Well, there's nothing that says that we couldn't shorten the time from application to giving the money in somewhere between 2 days to 7 days. Of course, this means that, yes, the application needs to be roughly correct when it's sent in, but it's a huge difference if you compare to what the lead time is today. And you can also make a guess of how many employees will they need in the future. I will not make a prediction. I will say it's very likely not 14,000. This is also an opportunity because it means that these employees can do other value-adding things. So is this a game changer? Well, as a business owner, this means that your business can work faster with lower cost of operations. And this, in the previous example, you saw a factor of 5 or 8 in speed improvement. But I want to pay attention to this one. This is kind of the area which I'm currently working in. If you look at this and the opportunity that exists, as an agile coach, maybe our approach shouldn't be to go in and do agile inside existing business processes. The approach should be to let's use AI to machine learn the crap of this problem instead of running agile change processes on progress on processes that are already suboptimal. And I could see that if you include AI inside this process, this is a reason why you might do a completely process re-engineer instead of just reusing the process as is. All right, small shameless plug here. We are trying to explore this area inside CRISP. So if you have a business challenge that you think could be solved using machine learning or AI, don't hesitate to talk with us and give us a notice. We have a small email. You can let us know, and let's talk. That's the basic idea. And we think this is useful because this we need to learn how to do this. Both, and I say this not only for us here, but also for the country in general. Let's stop there and take some time for some Q&A if I didn't waste all the time with the presentation.
We still have some time. Thank you very much, Mattias. That was really nice. We have one question in the chat. Can you tell us about interesting ways to remove bias from AI models? From Christian?
That's a very interesting question. Because it is a catch-22 question, because who injects this bias is actually the human that trains the model. So the AI doesn't inject bias. It's based on our selection of data, our selection of models, and how we tune the hyperparameters, and how we validate the model. That's where we inject bias. So I think the best answer to this is not look at the AI, but look at the person who trains the AI.
Thank you. If there are any other questions, feel free to write them in the chat, or maybe even just talk out loud. We're not that many people, 30 people in the room. We can handle that crowd, I think.
Just a curious question, if nothing pops up. How many of you have experimented a little bit with AI? Yeah. 3, all right.
I have a question. I'll shoot it in while people think a bit, if that's okay, even though I'm hosting here. So you mentioned deep learning, and you mentioned that it's more of a black box thing where you don't really see how it came to the conclusion, the result, the decision. And I have one experience from a client where this was not compliant. Basically, they had to be able to explain, and this was a regulated business, and they had to be able to explain how they came to the decision. And my question is, or my reflection maybe, is like, how is this even useful then in the public sector, where you often want to be able to be transparent and say, how did we come up with you? We decided that you are not allowed to get your sick pension or something. Won't you want to be able to explain that?
So this is a very interesting topic, which goes a little bit beyond the technology, but how we validate that this is useful, accurate, etc. And a spot-on example would be self-driving cars, because this is the case currently that this is a crux in this area. And the first thing to recognize that if you employ AI, this means a shift in the technology, a shift in how you see legislation, compliance, but also a shift in mindset. And I'll illustrate one of the mindset shift that will come. And the mindset shift is, we believe that humans always do a better decision. Now, if you employ AI and you can basically say, well, maybe the AI actually improves the decision because it makes it more accurate or quicker, this means you need to give away with this pre-assumption that we humans do a better decision, right? Okay, that said, if you look at the compliance situation, you're right that if you follow the current regulations in some areas today, you'll get the case where you say if you can't explain everything, we won't sign off on it. However, to deal with this case, you probably will need to find some fallback mechanism for some really interesting some edge security cases, like you run over a person, because that behavior, maybe you override the AI at some specific scenarios. However, this said, I can predict, or I make an assumption here, that the way that the compliance legislation thinks is, unless we can explain every single bit and byte, we can't understand what it does. Therefore, we can't sign off. What if, and this is where I think the legislation will need to move, and it's currently, very soon, is that if we can train a black box with and you can provide the testing that proves that it does what it should do, is it then necessary to go in and tell it how it figures this out? So if we can validate that it delivers enough accuracy on enough use cases, that's good enough. And maybe even a better evidence compared to if you do it with a human that randomly falls asleep or something like that. But that's making speculation where I think the compliance is being moved, and this is currently an ongoing conversation.
Thank you. So there's something here from Matthew Flynn or Ole, if you want to go first.
Yes, I just wanted to say that this deep learning, which is more of a black box, perhaps is not suitable for all kind of problems like social security decisions and stuff like that. They should be transparent and say that you don't get the money because you were sick 2 days, then you worked 1 day, and then you were sick 2 days again, or something like that. There are rules, and the system must be able to say which rules that apply to the problem.
I would still argue, Ole, that in this case, we can validate that the AI conforms to the rules that we set up by proving it in tests. But then it becomes philosophical, or moral, maybe ethical conversation. Is it okay if we prove this, or do I want to be able to explain this? And if you're right, Ole, if we do decide we want to explain how this came about, then deep learning isn't the right path, right?
Yeah. But there are other tools and frameworks.
Oh yeah. So this is an emergent area. A lot of things happening here right now.
And just a thought: isn't a lot of human decisions also kind of look at all the things and then make up your mind, not really logical, following the rules anyway? So maybe the deep learning is what's most similar to how we make decisions on ourselves. I mean, in terms of actually being able to explain how it was done.
It's a lot of things that's going to happen here. I can't make some really good predictions. But if you follow this area, there's everything from ethics, legislation, technology in here that. And of course, there is, of course, the point of, do we want to open this box for humanity? But I won't go in there. I will leave that to smarter people than me.
I think the last question here, maybe, or comment from Matthew. Ethical concerns abound. Who decides what a better decision is? This has been the subject of many science fiction stories and novels, the works of Asimov and Clarke. Nice references, by the way.
Very, very nice. I'll listen to opinions on this. I don't have a clear-cut answer.
Well, I mean, I'm just thinking it's a tough thing, and yes, there are no clear answers, but you get into the thing that the computer made this decision for me. The computer says no, and if you don't know why, the openness that you were talking about, was that the right decision? Was the bias that we talked about before of the folks who fed in the data such to prevent certain people from getting things that they should have? How do you know? And are there consequences to the computer making this decision? If a human made this, you can say no, slap them with a fine, slap them with a punishment. If a computer does it, who do you punish? Who do you make sure that it doesn't happen again? There's any number of approaches you can take to thinking about when you hand this off to a computer, what happens. Not saying it should never happen or doesn't happen, but it's what, I mean, if there's a car crash, is it the computer's fault? Is it the folks who programmed the computer's fault? Is it the driver's fault for not having his hands on the wheel to correct for the automatic driving system? Yes, or no. There's so many. So what do you do to the poor person on the other side who got killed by it? I don't know. In their family. So it is a touchy place to go. I think it is the thing. Do you open it? Well, it's already open. I think the cow's out of the barn, but how do you think about it going forward?
I like your analogies, and just give you an idea. I think that if this box is already open and we're dealing with the consequences right now, and if I would be in the legal area, I would think of using advice not in laws, because we are entering domains which we have not been to. I'm thinking maybe we should look at some philosophy or ethical, advice to figure out what to do in these areas today.
Thank you, Mattias. I think we should let that be the closing statements. It's 2:30 and we have time for our break. So thank you very much again. And thank you everyone for attending. I hope to see you here again in 5 minutes.
Thank you.